All right, I think we can solve this problem. It's saying that we have an asteroid, and the mass of this asteroid is actually equal to 8.9 e to the negative 4 times the mass of the Earth. And that revolves in a circular orbit around the Sun at a distance that's actually, and this is capital D here, this big long distance. Here's the distance from the middle of the Sun to the asteroid, and here's the distance from the Sun to the Earth, the little d and big D. Well, it turns out that the distance from the asteroid to the Sun is 3.3 times the size of the distance from the Earth to the Sun. We can actually sort of calculate these numbers real quick first, because we've got 8.9 e to the negative 4 times mass of the Earth, which is 6 e to the 24. So we should get that the mass here is 5.34 e to the 21. We can go ahead and write that right here, 5.34 e to the 21 kg. And then we'll do the same thing for distance. We've got that the 3.3 times 1.49 e to the 11th, that's going to be equal to 4.917 e to the 11th meters. Okay, I think we have enough information here. The first question it's asking is T is what? Well, we know that T for something in rotational, orbit here, this orbit, what do you call it again? Centrifugal motion. Something in centripetal motion is 2 pi r over v. And we know that velocity in orbit is actually going to be equal to the square root of m Sun divided by the, I think it's the orbit radius? Yes. Orbit radius. Okay. So this is tangential velocity. Tangential velocity. And this is the orbital radius, the orbiting radius. If we plug these two values together, then we're actually going to get T equals 2 pi r orb divided by the square root of gm Sun over r orb. Okay. Well, let's square both sides. So if we square this, we're going to get T squared equals 4 pi squared r squared orb. Divide this by g m Sun. And if we were to divide r orb again over here, we could actually multiply it to the top. So we're going to go r cubed orb. This is, in fact, the period of something in orbit. So that's kind of interesting. Okay. Now, let's go ahead and plug some values in. I think we have all these numbers because we have T squared is equal to 4 pi squared. And then what's the R3 of the orbit? That's MA. I think it's D. So what's this? 4.917 e to the 11th. And this is cubed. And then we're going to divide this by g, that's 6.67 e to the negative 11 Newton meters squared divided by kilograms squared. And then the final number here is the mass of the Sun, that is 1.99 e to the 30 kilograms. I believe that this will answer the question. Let's make sure that we square root this, because sometimes we make that mistake. So we're going to say 4 pi squared times 4.917 e to the 11th to the third power, divide that by 6.67 e to the negative 11th times 1.99 e to the 30. And I think this should work out. Get a nice little number here. Well, this is technically how many seconds it is. So 188.03587.9.4 seconds. And let's say we wanted to go 60 seconds, and this is in 1 minute, right? Then how about 60 minutes in 1 hour? How about 24 hours in 1 day? And how about 365 days in 1 year? because they're asking us for the years here. So we're going to divide this whole answer by 60 times 60 times 24 times 365, and we're going to get, yeah, turns out that the period is 5.96 years. All right, this is our answer for part A. So that's pretty good. Now what about for part B? It's asking for KEA over KE. Well, let's just scoot this down a little bit. We remember that there is the kinetic energy formula for something in orbit. That's just going to be, this is for the asteroid. I suppose we'll set up the ratio first. The KE in orbit is the mass of the planet times GM sun over 2R orb, which in this case, it's actually, here, I'll just erase it then. In this case, it's big D. That's the capital D here. And then we've got over here on the bottom, the mass of the Earth. I guess it's the mass of the asteroid here, the mass of the Earth. And then this is GM sun again, and then this is over 2 little d this time. This is the distance from the Earth to the sun. Now you'll notice that this actually cancels a whole bunch of good stuff out. It cancels G out, you cancel M out, this stuff is gone, and then T, this 2 is gone even. So we get that KEA over KEE is equal to M of the mass of the asteroid, and then this is actually divided by D on top here. And then over here on the bottom, we've got mass of the Earth divided by D. Well, we can put this back on top saying D over ME, get rid of that. And let's try to figure out what that is. So we've got mass of the asteroid, 5.34 e to the 21 kg, divided by 4.917 e to the 11, and then times d, which is 1.49 e to the 11, and then this is over 6 e to the 24 kg. And if we plug these numbers into our calculator, we've got that 5.34 e to the 21, divide that by 4.917 e to the 11th, times 1.49 e to the 11th over 6 e to the 24. And this gives us this interesting answer that basically the ratio of KE over, well, here, I'll put it in fraction form. 89 divided by 33, 4 zeros. Okay, so that's going to be our answer. And kind of a cool problem here. A little bit difficult, just having to understand gravity and centripetal motion and the equations that we have to use.